Last paper for grade 9. This is paper 1, and we're going to be looking at question 5 today, which is all about sequences. Okay, so if we look at question 5, they often ask this question to start with, where you've got squares or matches or some sort of shape like this. So in this question, a friend created a pattern using squares. In the first arrangement, she used 2 squares, in the second she used 5 squares, and in the third she used 8 squares as shown below. Study the pattern carefully and extend it by drawing a sketch showing how the squares will be arranged in the 6th pattern. Okay, so usually I find students are quite good at these ones. You've just got to keep drawing the patterns, just get a feel for what would be next, what would be the 6th pattern. Okay, so we can see in the first one, we've got 2 of these blocks going across. And then in the second one, we've suddenly got 2 of these vertical blocks. Third one, we've got 4 of these vertical blocks. Okay, so you can see that's going to be what extends. So every single time we get 1 more going across, and we get more of these vertical blocks. So I would just try and kind of draw the next one, so you have to excuse my bad drawing. But in the 4th one, what we would then get is we can see, okay, this one's got 1, 2, 3, 4. So the 4th one is going to have 5 blocks across. Okay, so 5 blocks across. And then we can assume there's going to be 1 on either side where there's nothing. So we can assume we're going to have something like that. So 1, 2, 3, 1, 2, 3. Okay, that would make sense to be the next block. Okay, so we had 1, 2, 3, 4 across. Now we've got 1, 2, 3, 4, 5 across, and we've got these 3 upper blocks. So then we can assume the 5th block, or the 5th set, is going to be something like this. So we're going to have 1, 2, 3, 4, 5, 6 across, and now we're going to have 4 of these. 1, 2, 3, 4, 1, 2, 3, 4. Okay, so that would be our 5th block, and then our 6th. You can see the pattern is just carrying on. Okay, so the 6th is going to be 1, 2, 3, 4, 5, 6, 7 across, and we're going to have 5 of these. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Again, apologies for the awful drawing, but you'll get the picture of what it looks like, and hopefully yours will be a lot better. Okay, so that is how we do these kind of things. We just try and play around, see how we can work that out. If we look at 5.1.2, now we're going to use a table to kind of work this out, and we want to know the formula that defines the sequence. Okay, so let's get some space here. So we can see we've got this pattern number and we've got the number of squares. So let's just get the number of squares. That's what's most important to us for now. Okay, so we've got kind of a sequence of like this. Sorry, where is my pen? Okay, so we've got 2, then we've got 5, then we've got 8. Okay, and we could carry on. We have now worked it out, how many squares there are, but with the drawings, but we don't need to. All we need to do, so if we want this formula, algebraic formula, how we always do it is the number in front of the n is this difference. Okay, so how do we get from 2 to 5? We have to add 3. How do we get from 5 to 8? We have to add 3. And we know, if we looked at our drawings, that it keeps going like that. So that is always how we get this first number. Okay, so the pattern is going to be 3n, and then we usually need to add something or take something away. Okay, so this n is what number in the pattern it is. So if it's the first pattern, the second pattern, the third pattern. So let's do a few tests to try see what that next number is. So if we wanted the first term, so t1, we're going to go 3 times 1 would give us 3. Okay, which is fine, but actually we can see our first pattern had only 2 squares. So we would have to take away 1 then. Okay, so that's how you kind of see. So this could be our pattern then. So t is 3n minus 1. Let's test it now and see if it works for all the terms. So for the second pattern, so t2, we're going to go 3 times 2 minus 1. And let's see, 3 times 2 is 6, minus 1 is 5. Okay, so we can see again, that gives us the right answer. And let's just check it for the third one just to make sure we're on the right track with this formula. So our third pattern, we're going to go 3 times 3, which is 9, minus 1 gives us 8, which again is the right number of squares. Okay, so that's kind of how you work it through. First of all, you always find the difference. That difference goes in front of the pattern number. And then you've just got to find out, do you need to add something, take away? Sometimes you don't have to do anything, but usually you do have to add or take something away to get back to this number in the your number of squares. Okay, finally we've got 5.1. Sorry, let's just scroll down a bit here. The last question we've got here is 5.1.3. Okay, well, not the last question, but another question we've got here. So let's have a look at this one quick. In 5.1.3, they say, okay, so use the formula that you've just determined to determine if the pattern number if there are 101 squares. Okay, so let's get this formula written down quick. So we said the number of squares. Okay, so that's our number of squares. Sometimes it's kind of difficult to keep track of this. So the number of squares is 3 times n. So 3 times the pattern number minus 1. So we want to know, what is the pattern number if there are 101 squares? So we're going to put 101 in here. So we're going to say 101 squares is equal to 3n minus 1. And all this is now is an algebra problem. So we're going to take this minus 1 across. It becomes a plus 1. So 101 plus 1 is 102. So 102 is equal to 3n. And again, we're going to take the 3 across now. We're going to divide by 3 because we were timesing by 3. So 102 divided by 3. Let's see, what do we get for that? 102 divided by 3 is 34. So n is 34. Okay, so then what that is telling us is that when the pattern number is 34, there are 101 squares. So if they asked you to draw the 33rd pattern, the 34th pattern, you would have 101 squares in it. I'm not going to try to draw that one. And then finally, 5.2, we've got a spider diagram or a flow diagram. Let me just get some more space here. These ones are pretty self-explanatory usually. So here they give us a formula and they give us some values to plug into the formula. Okay, so it looks scary. X is an element of this. They just want us to use these values. So what we're going to do is we have got this formula. So y is equal to 8x minus 3. And we are going to plug these values in. So we've got our x values on this side, and we're going to get our y values out. Okay, so if I plug in x is minus 2, all you're going to do is going to work out this formula with minus 2 as x. Okay, so what we would do then is we are going to say y is equal to 8 times minus 2 minus 3. And then we will get our y value out. So that's what they want. They want to know what y value do we get out when we put that x value in. And so we're going to see 8 times minus 2 is minus 16. Minus 3 is then minus 19. So we can see that's what we get for that top value. And we just go through like this for all of them. So then we've got when x is minus 1, again, same thing. I'll just write the formula here just so you get a feel for it. So y is going to be 8 times minus 1 minus 3. So 8 times minus 1 is minus 8. And then take away another 3 is going to be minus 11. Okay, you're going to do it for x is 0. So I'm not going to write this one down. You get the idea, but you're going to go 8 times 0 is 0. minus 3 is just minus 3. Then we've got for x is 1. So we're going to go 8 times 1 is 8. Minus 3 is going to give us 5. And then finally, when x is 2, so we're going to go 8 times 2 is 16. Minus 3 is going to give us 13. Okay, so that's all a spider diagram is. We just plug values in and see what we get out on the other side. I hope that made sense. Let me know if there's any questions I can go through, and thank you for watching.